Hi Irrelevance, this is Mr. Lim here again, and this is our second video in the aqueous solutions about the dissolving process. So let's get started. Alright, so this is what we're going to be learning about the dissolving process, what must occur, blah blah blah, those kinds of things. So let's have a look what must occur for a substance to dissolve. So to dissolve, a substance must undertake the following two things. They must break the bonds between solute particles. That means between the two solute particles, bonds must be broken, right? And they must break the bonds between solvent particles. Because if you think about it, right, if I have sodium chloride here in a ionic lattice of positive and negative ions, right, and I'm dropping it into some water molecules, right, here are all my water molecules, right, here are all my water molecules right here. They're all just floating around. Okay, I've got to separate out these ones apart from each other, and I'm going to separate these apart from each other to become something that looks like this, with all your water molecules separated from each other. Well, I mean, slightly more separated from each other, and your solute particles there separate. Okay, so you got to kind of slide in between those. So if these two things occur, then solute particles will embed themselves in the solvent and will form a mixture. Okay, so effectively you're sliding in like a ball pit. The solute particles are sliding in between the solvent particles. Both of these processes involve bond breaking and thus require energy. All right, so because they require energy, you've got to find some way to put those energy in. All right, let's move on. The energy to break the bonds during the dissolving process comes from the formation of new bonds between solute and solvent particles. Right? I don't know why there's no word between there. Between. Right? Solute and solvent particles. As they come into contact with each other and the kinetic energy the particles already have. Okay, so effectively, when a new bond is formed between solute and solvent, it'll produce energy, and whether that energy is sufficient to break the bonds between solutes and solvents, then you're going to have the dissolving process occur. All right. So as the surface of the solute particles interact with the solvent, they release energy, which can be used to further disrupt bonds between the solute, and the solvent. So what that's saying is that when you initially start with your salt block here, right, so here's your salt block inside this water here, right? Sometimes you're going to have interactions between the two, the solute and the solvent, on the surface, and that's going to create energy there, right? And that creation of energy is going to be used to break the next bond, break the next bond, break the next bond, so on and so forth. Okay, so you're effectively going to create energy to break the bonds between the other particles and therefore become dissolved. So this can lead to more energy being formed and lead to the eventual dissolving of the whole solute. So it's those initial breaking of the bonds between solute and solvent on the surface, which provides the initial point of energy, and then as they break more and more and more, they produce more energy to go dissolve more and more. All right. Thus, dissolving will occur only if the process of solute-solvent bond formation, now this is the important part, produces sufficient energy to break the bonds between solute-solute and solvent-solvent. Okay, so the idea is that they need to produce enough energy to break those bonds there. All right, so let's have a look at a couple of examples. Okay, so let's take ethanol in water. So ethanol is this substance here, right, with hydrogens here and here and here. Okay, so between the solute and solute bonds, which is the ethanol, okay, and I'll just use a different color for water. Come on. We use a different color for the water, right? The solute-solute bonds are dispersion forces, dipole-dipole, and hydrogen bonding. So between these this molecule and another one of itself. It's going to have hydrogen bonding because of that, and it's going to have dispersion forces because of this, right? But generally, it's going to have all three types of bonding, and it's important to list out all three types of bonding, okay? The solvent-solvent bonds, which is the water, are why am I going that way for? Let me get back, please. All right, so the solvent-solvent bonds are dispersion, dipole-dipole, and hydrogen bonding. Now, you've noticed that I've said dispersion, and it's small amounts of dispersion force, right? Because this hydrocarbon chain on the ethanol and the water molecule itself are reasonably small things, so the dispersion forces here are reasonably small, right? So you're not going to have a large amount of dispersion force, and the predominant force is going to be hydrogen bonding. Now, when these two substances come together, they're going to form the following. So when the solute-solvent bonds, we'll use this yellow, right? When solute-solvent bonds are formed, they are dispersion, small, dipole-dipole, and hydrogen bonding, because there can be hydrogen bonding between this H and that O there. All right, so hydrogen bonding between those two substances. So you'll notice that the solute-solute, solvent-solvent, and the solute-solvent bonds are all effectively the same, right? Which means that they're going to produce enough energy. The amount of energy released during bond formation is roughly the same as the energy required to break the bonds between solute-solute and solvent-solvent, right? So that's just saying that the amount of energy produced is roughly the same because the bond strength is roughly the same. But you can't just say bond strength, you have to say the energy produced, right? That's the amount of energy released by the solute-solvent. Bond formation is sufficient to break the solute-solute and solvent-solvent bonds, and thus ethanol is soluble in water. Okay, so those bonds' strength is roughly the same, so the energy released is roughly the same as the energy required to break. Okay, so the important ideas here are that you've listed out these different types of intermolecular forces between solute-solute, solvent-solvent, and solute-solvent. You've made a description of the bond strength and thus the description of the bond, the energy that's released during bond formation and the energy that is required during bond breaking, and how they're roughly equal or not equal. All right, let's have a look at another example. Hexane in water. So hexane is this with all hydrogens here. Okay, so they're just all hydrogens. You can use your imagination. So your your solute bonds are dispersion only. Now, because there's no OHs or anything on this one, it's just dispersion forces, and because it's a reasonably large, 6 or more, it's a large amount of dispersion force. All right, much larger than a smaller molecule. Then we go to the solvent-solvent bonds, which are trying to be water. So we're trying to dissolve that in water, is going to be small amounts of dispersion force, dipole-dipole, and hydrogen bonding. And the solute-solvent bonds, now, can water form hydrogen bonds with this hydrogen here? Can that form hydrogen bonds there? No, it cannot, because that hydrogen is not positive enough because it's not bonded to a very electronegative element, right? So the only type of intermolecular forces between solute and solvent are just going to be dispersion forces. And they're going to be small because the dispersion force is based on the smaller molecule, which is the water in this case. So the amount of energy releases in the formation of these dispersion forces is not equivalent to the energy required to break the bonds, right? So the bonds formed here are quite weak, right? Compared to the bonds between solute-solute and solute-solvent. Thus, the amount of energy released by the solute-solvent bond formation is insufficient to break the solute-solute, solvent-solvent bonds. Thus, hexane has a low solubility in water. All right? This is not to say, remember that, the idea that you will be able to dissolve some of it in there. Some of the solute-solvent particles will have sufficient energy because maybe, remember, each solute and solvent has a range of energies, and some of them will just naturally have more energies than others and therefore can dissolve, but not many, right? So it's only going to be a small proportion. All right, next example. We've got octanol in water. So octanol, I will draw it, not even any space here. I'll draw it over here. C, 1, 2, 3, 4, 5, 6, 7, 8. It's octanol. I really should say it's one octanol, but there you go. There is a OH on it, and the rest of it is all hydrogens on the outside. Okay, so the solute here, it has dispersion, large. Why has it got large dispersion forces? Because it's got a large hydrocarbon chain there, right? It's got dipole, and it's also got hydrogen bonding. So it does have hydrogen bonding between those things there, right? The solvent-solvent bonds are dispersion, small, dipole, and hydrogen bonding as well. The solute-solvent bonds are dispersion, small, dipole, and hydrogen bonding. So you'll notice that, whoops, I should have been green. You'll notice that they have the same intermolecular forces for the bond breaking and the bond forming. However, there is one difference. This one here has large dispersion forces, which, are generally quite strong. And remember that dispersion forces can be larger than hydrogen bonding if your dispersion forces are large enough. And when they're 6 and above, it's generally large enough to be stronger than hydrogen bonding. 6 carbons and above are generally stronger than hydrogen bonding. So this dispersion force is large then. So now let's have a look at what happens then. The amount of energy released in the formation of these dispersion forces, small, dipole, and hydrogen bondings, would be enough to separate solvent-solvent bonds, that's the bonds between water, but not the solute-solute bonds. That's the bonds between the octanols. Right? So as the molecules get larger, their dispersion forces increase, and then it gets harder to break the bonds between them. So generally, solubility of hydrogen bonding molecules in water decreases with increasing size. So as your if you've got hydrogen bonding in a substance, but as it gets bigger, the solubility in water will decrease because you've got that increasing dispersion force. Right? So at around 6 carbons long, the dispersions are large enough to bring the solubility to a very low point. Okay? So the idea is that once you get it 6 carbons long, the dispersion force is too large for any hydrogen bonds that you form with water to overcome those dispersion forces. Okay? Say that again. Once you get too long, the dispersion forces get larger. Even if you form hydrogen bonding between the solute and the solvent, those hydrogen bonds aren't going to be sufficient to break the dispersion forces between the large molecule. Thus, the amount of energy released by the solute-solute bond formation is insufficient to break the solute-solute and solvent-solvent bonds, and it has low solubility in water. Low solubility in water. Let's have a look again. Sodium chloride. So sodium chloride is your solute, water is your solvent. Your solute bonds are ionic and dispersion. Remember, everything has dispersion, even ionic substances. All right? So ionic bonds and dispersion. Solvent-solvent are the normal dispersion, dipole, hydrogen bonding. Now we have solvent-solute bonds are known as ion-dipole bonds, or also known as ligands. Okay? So it's effectively a bond between an ion and a polar molecule. So ligand bonds are generally very strong, but depend on the ionic substance. Okay, so here is a sodium molecule, sodium ion, and a chlorine ion, right? And water will arrange themselves in a specific way. Let's have a think. Would it arrange itself this way, or would it arrange itself this way around the sodium? Well, the sodium is a positive ion, so the negative parts of the water molecule should be attracted to it, which means that this one at the top here is not the way that it's going to be orientated. It's going to be orientated with the negatives towards it, right? And you can draw out your ligands as like in the similar way that you draw out hydrogen bonds there, and make sure that you label them as ligands. Okay, so those ligands form when you have ions within a polar substance. For the chlorine, the water molecules would rearrange themselves in the opposite way so that the positive end of the water molecules would be close to the chlorine. Okay? Okay, and then you can draw your ligands there as well. Okay, so sodium chloride is soluble in water, so that tells us that the energy released is greater than the energy required to break those bonds. Now, it's important to remember that ionic substances have different solubilities in water, and we'll go through that in another video. So you will learn later how to determine if an ionic substance is soluble, and from that, you can infer the amount of energy the ligand produces compared to the energy required to break the ionic bonds. Right, so in sodium chloride's case, the ligands produce enough energy to break the bonds between sodium and chlorine, but sometimes the ligands that are produced do not produce enough energy to break the ionic bonds between the two ions, right? So that will determine its solubility, and we'll go through that idea in another video, right? But generally, we talk about it in this way for ionic substances. Last one, butane in benzene. So we have butane is our solute. We now have a different solvent. Instead of water, we have benzene, right? So we are dissolving it in something different. You should hopefully remember what butane and benzene are. I'm not going to go through those. So what are the solute-solute bonds? Solute-solute bonds are dispersion forces, medium, right? So 4 carbons, medium-ish, right? Solvent bonds are also dispersion forces, and you would say medium-large because benzene is like a 6 carbon anyway, right? And the solute-solvent bonds are also dispersion forces. So the amount of energy released in the formation of the solute-solvent bonds, which is that dispersion forces, is roughly the same as the solute-solute-solvent-solvent bonds. Thus, the amount of energy released in the formation of solute-solvent bonds is sufficient to break the bonds between solute-solute and solvent-solvent and result in a high solubility in benzene of butane. All right, so that's generally how that works. And dispersion forces, because they're all kind of the same, most dispersion-only substances will dissolve in other dispersion-only substances, regardless of the size. Okay, so even if the one is a very large one is a very small one, it'll still dissolve. However, you will remember that at room temperature, the larger the solvent, there's more likely that it's going to be in solid form rather than in liquid form, and so therefore, like, you're not going to really have, it might stay in solid form and not dissolve. Right? Okay, so one couple of last points, okay? It's important to always discuss the explanation about solubility, the size of the dispersion forces involved. So talk about whether the dispersion forces is small because it's a small molecule, medium or large, and the amount of energy released and required. Don't just talk about the strength of the bonds. Don't just say that that bond is strong, therefore it doesn't dissolve. You have to say that bond is strong, therefore it requires a large amount of energy, and insufficient energy is produced because the bonds that are produced are weak or something, and therefore don't produce so much energy, and thus it doesn't dissolve. Okay, talk about energy release rather than just the strength of the bonds. All right, and that's it. Adios.